Hey there. So, I read this blog from the gaffer on Mass Bandwidth, calling on an interview challenge about how you would set up 1 million clients sending 100 bytes each, 100 times a second, and a server that responds with the FNV hash of that data. In this video, I'll take you down the rabbit hole that I went down, reading and learning about how you get this insane challenge going. But first, a disclaimer. He mentions himself that this is kind of an impossible problem. And I agree. You can read more on the GitHub repo linked in the description, but we can get estimates based on running tests and figuring out how to push this setup to the limits. He specifically asks for Golang, but I think Rust, in one of those rare cases, actually proves a slight advantage in what we are attempting to do. Unless of course you decide to use XDP, in which case you're still not using Go. I'll make another video talking about XDP and how awesome it is. Don't forget to subscribe so that you get notified when we get to those. Let's begin by setting up a simple server that receives a UDP packet and responds with the FNV hash of the data. What's FNV? It stands for Fowler Nolvo hash. In this particular situation, I imagine it stands to be a sort of proof of computation, something for the server to do with the incoming data. It could be replaced, for example, with computing the movement of a player based on incoming inputs and respond with the new state. We can set up a Tokyo UDP listener that accepts the incoming data, passes it to the FNV hash function, and returns the hash to the incoming packet's address. Let's use the clap crate to parse the port to listen to from the command line. On the client side, we can ignore the creation of the data and use a fixed array of 100 bytes that is sent. We can create a new UDP socket on a random port, start a timer, and using a select block in a loop, send this data on every tick. We can also listen for incoming data in the same select block and use that to process the returned FNV hash. In this particular situation, I'm using an atomic uint64 to keep track of how many packets were sent and how many were received. Lastly, let's start a bunch of these clients inside our main function. We can control this using a command line parameter. Thanks clap for being awesome. We can also pass in our server address and the sending frequency. Let's run it. On my 6-core 12-thread machine, you can see that we can comfortably run about 500 clients before we start losing packets. Not bad, but not great either. First off, let's look at how to improve the server. You might notice that the server is effectively listening on a single thread. Maybe we can launch multiple server instances on different ports and let the clients connect round robin to each of them. Not a bad idea at all, but it can become an orchestration nightmare. That's where a Linux sockets trick comes in. We can actually start multiple servers listening on the same port and let the kernel decide which one of these to send packets to by setting the so_reuse port. I use the sockets2 library to be able to set these Linux specific socket params and then pass that socket into the Tokyo UDP socket. This now lets us boot multiple servers that can now respond with the hash on multiple threads. We replace the single server block in the main with a loop that starts multiple servers that listen on the same port. Running this code, we can see that we can push the numbers way higher, 3000 clients easy. As we push more clients on this, we hit our first limits, file descriptors. Everything is a file on Linux, and so when we open sockets, they use up the allowed file descriptors and we run into the soft file descriptor limit immediately. On my computer, it defaults to 1024 and that is just not enough. We can update those by updating the limits.conf file. You can also set limits using the ulimit command. The kernel also keeps a memory buffer to hold in-flight packets, one for incoming and one for outgoing packets. We should definitely increase that so that we can safely send and receive more. Otherwise, the kernel just drops the incoming and outgoing packets at the point we go past this buffer. We can also use socket2's set, receive and send buffer size for particular sockets. All of this takes us to almost 6000 clients. Time to figure out how to go faster. Cargo FlameGraph can tell you where your program is spending its time. Running a client and server with FlameGraph, we can see that at this point, most of the time is taken up by the Tokyo scheduler. Work stealing might not be the best idea for this use case. This is where I think Rust has a definite advantage over Golang. We can choose our runtime and switch to a thread per core runtime, something like glum.io or mono.io. Mono.io is a thread per core Tokyo alternative from ByteDance, the guys who made TikTok. It uses IO Uring for tackling async syscalls. IO-Uring, for those who don't know, is an extremely fast async IO API in Linux that lets us use a zero-copy ring buffer to read, write data between user space and the kernel. We had to make a few modifications for the mono-IO replacement. Most notably, some of the data now needs to be thread local. I also removed all select statements and instead used the mono-IO interval to actually yield the threads when it's not time. On the receiving end, we don't change much, replacing Tokyo's UDP listener and sender with mono-IO's IO-Uring version of the same. I added a thread count param to both the server and the client and then spawned as many threads running the mono-IO runtime inside them. To boost this further, we can use the utility function supplied with mono-IO to pin our threads to specific cores. This will improve cache locality of the data as the same data in socket is processed on the same thread. Well, this is surprising. The mono-IO version is slower. It's processing way less than 6,000 clients, even though it's managing to send 60,000 packets. I probably messed up my implementation. You guys tell me, maybe 6 cores isn't enough to actually test the difference. I would like to talk about Hetzner at this point. I've been using this cloud provider for a few years now, and truly nothing beats their pricing. I sincerely believe that egress pricing is the biggest scam pulled on the developer world, and I was extremely happy to discover Hetzner because they don't have such predatory and unfair practice. You get truly generous egress limits and very powerful cloud computers for a fraction of the cost of AWS or Google Cloud. This is why I decided to test out my setup on Hetzner Cloud. They also switched to per hour billing recently, which means I do not burn a hole in my pocket while testing this. I can start and stop servers while I test the system. I got 2 of the AX series servers and connected them to each other using a virtual switch. Now they can talk to each other directly with local IPs. There's also a 10 gigabit NIC between the two that I ordered separately. I'm aiming for greatness here. My build process is simple. Push to GitHub, pull from GitHub, build and test. I start the server on one side and spawn the client with a very high client count on the other. These machines are 12 cores each, and I expect to see much higher numbers than my local machine. And surely enough, look at that go. After a limit though, I can see that it starts to drop packets even though CPU usage is still above 60% according to HTOP. So what's happening? As outlined in the Cloudflare blog about receiving 1 million packets, I got past another hurdle by modifying how the NIC sends data to my server threads. By running this ethtool command, I can tell my NIC to send packets to the same thread based on the IP port hash of the sender and receiver. Oh, that bumped up packet count by a lot. At this point, we are receiving from about 15,000 clients at the rate of about 1.5 million packets. This is on 2 $45 machines with a $17 NIC in between them. Scaling that to 1 million clients would be about $7,300 a month. I can highly recommend using Hetzner for some reduced costs. I have one more trick up my sleeve though, XDP. With XDP, you can write eBPF programs that run directly in the kernel. There's a bunch of restrictions that you need to be mindful of, and I'll link the videos that talk about it in the description. Rust has support for writing XDP programs as part of your normal application through a wonderful tool called Aya. Let's do it. We can use the Aya provided template to instantiate an eBPF compatible Rust project. Once that is done, we can focus on writing the actual XDP layer in Rust, where we calculate the FNV hash in the kernel and respond immediately. At this level, you're receiving raw packets, not yet processed by the kernel. So you need to read the packet headers and pull out sender address and data through reading raw bytes. In our case, we swap the sender and receiver information and replace the payload with the hash, giving the packet back to the network interface by using XDPTX return value in the XDP function. The network card then sends the packet out. It never touches your user space program. We gain another 1,000 clients, reaching about 16,000 clients. But look, the server isn't breaking a sweat. If we batch send 10 packets per client, we can reach even higher number, like nearly 2 million packets. Now if we could just make the clients use XDP as well, that's going to be insane. But that's for a future video. If you guys have any other ideas, do let me know in the comments below. The code for all of this is in the description. Looking forward to hearing from you. I'm still here. Cheers.